So we're back to the chapter linear congruence. So before the first part of the video, we just study one particular example, 2x equal to 12 modulo 6, and we know how to solve it. In particular, we also discuss there are some solutions which are not congruent, okay, incongruent solution. So how do we find all those incongruent solutions? Um, and how many of them? So that is back to the proof of the theorem. Okay, after we finish the proof, we will see why that has to be true. So now we are doing the proof. Okay, now again, remember we let D to be the GCD of A and M. Okay, so and we are studying the problem ax equal to b, a congruence to b modulo m. Okay, so this is what we are doing. Okay, now actually if you let me just go back a little bit. So you check the theorem. Okay, there are two parts. So if the GCD is not divisible b, then in fact this problem, this equation has no solution. Otherwise, this problem will have exactly d many incongruent solutions. Okay, so that is the problem. Now, as before, we call that equation to be star. Okay, just for discussion purpose. Okay, we let that equation to be star. Now let's just do the easy case. Okay, so suppose D is not a divisor. Okay, divisor of B. Okay, then let's see what happened. Then we argue by contradiction. Okay, so we argue by contradiction. That means we assume the problem has a solution. Now suppose, now if ax equal to b modulo m has a solution, then let's see what happened. Then the consequences is then there are x and y, x0 and y0 I should say, okay, such that we have ax0 plus my0, okay, 0 equal to b, right? Because if that equation has a solution, that means we have some x0, okay, satisfying ax0 equal to b, I mean congruence to b modulo m. In particular, that congruence relation, you can rewrite that into this linear Diophantine equation. Because what is the meaning for congruence again? Congruence means ax minus b is a multiple of m. Okay, and I just call that multiple to be y0, right? Then if we have that, this is the consequences. Okay, this is exactly the linear Diophantine equation. Ax0 plus my0 equal to b. So we have this equation. Now what next? Now you see that, okay? Because remember, what is D? D is the GCD, right? If D is the GCD of A and M, then D must divide A and B. Sorry, A and M, right? Because by definition. Then this left-hand side will be always divisible by D, right? Because you can pick out, you can factor out the D, so the left-hand side is just a multiple of D. That means because left-hand side equal to right-hand side, but the right-hand side is B. That means B is also a multiple of D. Then there is a contradiction because we assume D is not a divisor. Okay, so let me just save my words again and just say which is impossible. Okay, so just understand why. Okay, then first case is easy. Okay, as I said, if D is not a divisor, then no solution. So in fact, no solution for star. Okay, so that is the first case. Now, on the other hand, suppose now we have D is a divisor, divisor of B. Okay, then what can we get? Then for the linear, okay, then for the linear Diophantine equation, what equation? Ax plus my ax plus my equal to b. Okay, so we look at another problem. Okay, we just simply look at the linear Diophantine equation ax plus by equal to b. Now remember, if D is the divisor for B, then for that linear Diophantine equation, we learned that already. Then what is the consequences? The consequences is this linear Diophantine equation must have infinitely many solutions. Okay, so the linear it has infinitely solution. Okay, and in particular, whose variable x is given by this x equal to x0 plus plus m over d times t. Okay, for t being any integer. Now what is x0 here? Actually x0 plus y0, so we have two actually, x0 and y0. This satisfies ax0 plus my0 equal to b. In fact, that x0 y0 is just a solution for the linear Diophantine equation, because as I said, we know how to solve it, and it has infinite solution. In particular, it must have at least one. Now how can you get this one? Well, you can use Euclidean algorithm to get one solution, x0 y0. Okay, and remember we have even more. Okay, we know the form for the solution. The solution is in this form. Okay, and here, because the original problem, it just have one variable, which is x, so that's why we can sort of ignore the y variable. We just consider this part. Okay, anyway, so we got this solution, but now we don't know how many, right? Yeah, we don't know how many, right? So but at least hence this x equal to x0, let me just copy and paste. Okay, so this part is the solutions, I should say, solve the original problem, solve star. Okay, at least we know that it solved the problem, because you can check it directly. Okay, it must solve the problem. Okay, now because not k, t. Okay, I'm using t here. T is any integer, right? So you can change. You can pick some particular choices for t. Okay, and then you get some solutions. Okay, for example, so note that for t equal to 0, 1, 2, okay, up to this number, d minus 1, okay, still x equal to this number still solves, because I just choose some particular choice for t. Okay, solve this ax equal to b modulo m. It's always true, right? We just pick some particular choice. But now I want to show this, okay? We want to show that, in fact, actually those value t equals 0, 1, 2, up to d minus 1, if you substitute it back to the solution, they are the only incongruent solution to the problem, okay? Now, of course, you can find any other solution, but any other solution will be congruent to those solution. For some solution, you pick it for t equal to 0, 1, 2, or up to d minus 1. So that means there are only d many incongruent solution. Rather than these d incongruent solution, any other solution will be congruent to one of those members. Okay, no matter how hard you try. Okay, and let's see why. Okay, we want to show that the solution given by, okay, let me just, okay, do that. Given by, okay, go back a little bit. Okay, given by x, okay, copy and paste, right? Given by this for t equal to this, okay, again, copy and paste, are the only incongruent solution to ax equal to b modulo m. Okay, actually they are the only incongruent solution. So let's see why. Okay, now there are two parts. Okay, you have to show. First, you have to show they're incongruent. Okay, the other thing is you have to show if you have another solution, okay, then that solution must be congruent to some of those members, those d members. Okay, this is these are the two things you have to prove. So let me just do it in this way. So part one. So first, to see why, okay, they are incongruent. Okay, they are incongruent. Now, if we have, okay, again, actually, we sort of argue by contradiction. Suppose we have two members, okay, so say this, okay, so I mean T1, okay, so just some member T1 that is congruent to another member, let's say T2, okay, and this is true for congruence modulo M with, of course, T1, T2, they are coming from the set, okay, from the set 0, 1, 2, up to d minus 1. Okay, so that means I'm saying, okay, what I'm doing here, I just pick any two members from those solution. Okay, I pick those T1, T2. Okay, I choose those T1, T2 from the set 0, 1, 2 up to d minus 1, and I said, well, if they're congruent, then what happened? Okay, actually, this is, as I said, is the method of argue by contradiction, because I want to show those members must be incongruent, but I first assume they are congruent. Okay, so again, let me just say, we argue by contradiction. Suppose not, and we have. Okay. Now, but you have to be careful, because I'm saying, okay, they are incongruent and they are two different members, right? So I have to say they are different, okay, and it's different from from T2. Otherwise, nothing to say, right? Because if they are the same, then of course they are the same. I mean, if T1 and T2 they are the same, then the corresponding solutions they must be the same because everything are now identical. So they must be different. And I'm saying, okay, if you have two members, different members, if they are congruence modulo M, then there must be something wrong. Let's see why. Okay. Now, by the congruence relation, okay, they're congruence, right? So in particular, you can cancel the x0 on the both sides because x0 appears on the left and on the right. So you can cancel it. Then we have this, okay? So we can copy that, okay, and then clean up this x0. And we still have congruence relation modulo M. But what is the meaning? Okay, remember what is the meaning for being congruence, which implies that we have this, okay? If we drop out the congruence modulo M, then we have to add back some number. For example, we add n m, which is a multiple of m, okay? That means why they're congruence? Because the difference is a multiple of m. Okay, so which implies that they are equal, but with a multiple of m for some integer n. Okay. Now this is the equation. This is the equation, right? So there's no congruence for that equation. So you can do whatever you like. Okay, for example, you can multiply numbers, you can divide numbers. Now remember, if you have a congruence equation, okay, if you have a congruence equation, you are not allowed to divide numbers. I mean, in the sense that you're not that free to divide numbers, okay, because there are quite a lot of examples, okay, that if you have two numbers being congruent, it doesn't mean that when you divide that by some number, they're still congruent. Okay, that is important. Otherwise, you might have something wrong. So let me show you one example. Just digress a little bit. Okay, just a small remark. Okay, notice that in general, if two numbers are congruent, for example, AC, let's say CA is equal to a congruence to CB modulo M. It doesn't mean that we have okay, sorry, I typed it wrong. CA congruence to CB. It doesn't mean that we have A congruence to B modulo M. That is wrong. Okay. Example, a very quick example. So